Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. This is the third module of the course. The title of the third module is Equations of Change. In this module we will be having two lectures. One lecture would be Equations of Change for isothermal systems, and then another lecture would be Equations of Change for non-isothermal systems. So, in this lecture we will be deriving equations of change for isothermal system. So, what are they? They are the conservation of mass and then conservation of momentum for a isothermal system. So, now we go into the derivations of these two equations in this class and then see their limiting conditions. So, let us start with the conservation of mass, which is also known as the equation of continuity. So, now let us consider a flow system of your interest where the fluid is flowing. Flow space you divide into the small control volumes. They should be small enough so that the property within the control volume should be constant or uniform throughout the control volume, and then they should be large enough so that the large number of molecules can be accommodated in those control volumes, so that they can have infinite number of interactions amongst them to maintain the local thermodynamic equilibrium. So, now out of this subdivided system, you consider one control volume of the size delta x multiplied by delta y multiplied by delta z. Now, here in this control volume, if you do the mass balance, so the mass balance would be rate of mass accumulation is equals to rate of mass in minus rate of mass out. If there is no accumulation, then rate of mass in minus rate of mass out should be 0. So, now mathematically we derive equations for a microscopic system here where the continuum hypothesis is valid. So, let us complete the control volume that is shown here. So, what I am doing? I am just completing it by extending these lines. So, now this x direction, this is delta x, size of the control volume in this x direction is delta x, and then in the z direction this size of this control volume is delta z. Similarly, in this y direction it is delta y. Now, let us consider first this plane that is perpendicular to the x axis, so that to consider what is the rate of mass in through this plane or through this phase, right, and then similarly the other side of this control volume in the x direction, that is a location x plus delta x, what is the rate of mass out, that we have to mathematically represent. So, now here the actually mass is entering and leaving in all three directions, x direction, y direction and z direction. So, we have to write this rate of mass in quantities and rate of mass out quantities in all three directions, and then accordingly we have to substitute in this balance equation. So, in the x direction, what is the rate of mass in at location x is rho v x at location x multiplied by the area of this shaded face is delta y multiplied by delta z. So, the rate of mass in at x location in the x direction is rho v x multiplied by delta y delta z. Similarly, rate of mass out at location x plus delta x, this is x plus delta x location, right. What is the rate of mass out? So, then that would be through this phase that mass is going out. So, that should be the rho v x at location x plus delta x, and then it should be multiplied by the area of the phase through which it is going out, that is delta y multiplied by delta z. So, rate of mass out in the x direction at location x plus delta x is nothing but rho v x at x plus delta x multiplied by delta y delta z. Similarly, in the y direction, rate of mass in is rho v y at location y multiplied by delta x delta z. Delta x delta z is the phase through which mass is entering in the y direction, and then rate of mass out in the y direction is again rho v y at location y plus delta y multiplied by the area of the phase through which it is going out, that is delta x delta z. Now, similarly, if you take in the z direction, so let us say this is the z direction, location is at z location, right. So, what is the mass is entering here is rho v z at location z, and then what is the area of the plane through which it is entering in the z direction is the area of this particular plane, that is delta x multiplied by delta y. So, rho v z at z multiplied by delta x and delta y would be the rate of mass in the z direction. Similarly, rate of mass out in the z direction at location z plus delta z is nothing but rho v z at location z plus delta z multiplied by the area of the phase through which it is leaving out, delta x multiplied by delta y. Now, we have this net rate of mass in all three directions, that is rate of mass in minus rate of mass out in all three directions. So, we add them together and then equate the summation to the rate of mass accumulation. So, when you do this rate of mass accumulation is nothing but dou rho by dou t multiplied by delta v, that is delta v is nothing but the control volume of this control volume, that is delta x multiplied by delta y multiplied by delta z. So, when we include these terms here, so in the entire control volume this is the rate of mass accumulation, and then this is the net rate of mass flow in the x direction, this is the net rate of mass flow in the y direction, this is the net rate of mass flow in the z direction. Now, what you do? You divide this equation both sides by delta x, delta y, delta z, and apply the limiting conditions delta x tends to 0, delta y tends to 0 and delta z tends to 0, so that you can apply partial derivative principles. So, when you do here, so left hand side you have only dou rho by dou t, right hand side you have rho v x at x minus rho v x at x plus delta x divided by delta x plus second term similarly in the y direction rho v y at location y minus rho v y at location y plus delta y divided by delta y plus similarly in the z direction rho v z at location z minus rho v z at location z plus delta z divided by delta z. Now, for these three quantities, if you apply the limiting condition delta x tends to 0, delta y tends to 0 and then delta z tends to 0, you can write them as the minus dou by dou x of rho v x and then minus dou by dou y of rho v y, then minus dou by dou z of rho v z. So, when you simplify this equation, you can write dou rho by dou t is equals to minus of dou by dou x rho v x plus dou by dou y rho v y plus dou by dou z rho v z. This is nothing but continuity equation. This is nothing but the continuity equation in the Cartesian coordinate system. So, vectorially this equation can also be written as dou rho by dou t is equals to minus del dot rho v. This whatever del dot rho v is there, that is also known as the divergence of mass flux or divergence of rho v. So, this continuity equation simply describes the time rate of change of fluid density at a fixed location, at a fixed point. So, for a constant density system like incompressible fluids, this continuity equation can also be written like del dot v is equals to 0 or divergence of velocity is equals to 0. This can also be written for a constant density system. Now, this is how the continuity equation one can derive in the Cartesian coordinates, and then this is given here once again. Similarly, one can develop these equations in the cylindrical and then spherical coordinate system also. In cylindrical coordinates, the continuity equation is dou rho by dou t plus 1 by r dou by dou r rho r v r plus 1 by r dou by dou theta rho v theta plus dou by dou z rho v z is equals to 0. Similarly, in spherical coordinate system, this continuity equation is dou rho by dou t plus 1 by r square dou by dou r rho r square v r plus 1 by r sin theta dou by dou theta rho v theta sin theta plus 1 by r sin theta dou by dou pi rho v pi is equals to 0. So, any problem, any momentum transfer problem if you are solving, the solution, whatever the velocities that you find out after solving all these equations, that velocity should satisfy this continuity equation. If the solution velocity profile is not satisfying this continuity equation, that means that velocity profile obtained velocity profile is not reliable, it is not accurate. So, one has to recheck the solution if the velocity profile is not satisfying the continuity equation. Now, we develop equation of momentum or equation of change for momentum. So, this also we do in the Cartesian coordinates, and one can similarly do the same thing in the cylindrical and then spherical coordinate system also. So, whatever the flow is occurring in the system, that system you subdivide into the small control volume, and then those control volume should be small enough that the property within the control volume should be uniform, and then they should also be large enough that the within the control volume, each control volume, large number of molecules should be accommodated, so that they can have infinite number of collisions amongst them in order to maintain the local thermodynamic equilibrium, which is also essential condition for this continuum hypothesis. So, out of this control volume, several subdivided control volumes, let us consider one control volume as shown here picture. If you apply the momentum balance for principle for this control volume shown here, so what you get, a rate of accumulation of momentum is equals to rate of momentum in minus rate of momentum out, plus if any external force is acting on the fluid, like gravity or electric field or magnetic field, etc., those external due to the external force, any additional terms are there, they should also be included in the right hand side term. If at all they are affecting the momentum transfer process, they should be included in the right hand side term in the right hand side of this equation 1. And then since we know that fluid is moving through all 6 phases of this control volume shown here, there will be 3 momentum equations in each direction, x direction, y direction and z direction. So, what we do? We derive one particular x component of momentum equation, and then analogously we can write the y and z direction momentum equations. Then we know further that this momentum can enter and then leave the control volume by 2 mechanisms. One is the convective transport mechanism, another one is the molecular transport mechanism. So, in order to reduce the mathematical writing several times, what we do, we define one particular combined momentum transport flux pi, rather than writing this momentum flux due to the convection, momentum flux due to the molecular mechanism in out several times like that, we write one combined momentum transport flux pi, and then we do the derivation of the equation, and then finally we substitute for all this mechanism, all these individual contributions due to the convection and then molecular mechanism. So, now this is the control volume here, right, horizontal x direction, vertical z direction, and then this way this is the y direction. So, combined momentum transport flux tensor whatever is there, that pi we have defined now, right. It is due to the both convection and then this pi is having the both contributions of convection and then molecular mechanism. So, now the x component of momentum entering at x location would be pi xx at x delta y multiplied by delta z. Similarly, the x component of momentum leaving through the phase at x plus delta x location is again pi xx at location x plus delta x, x plus delta x, right. So, the area of the phase through which it is leaving is nothing but delta y multiplied by delta z. So, pi xx at x multiplied by delta y delta z is the x component of momentum that is entering at location x shaded phase x, that is shown here, and then pi xx at x plus delta x multiplied by delta y delta z is the x component of momentum that is leaving in the x direction at location x plus delta x. Similarly, rate at which x momentum enters and leaves the phases at y and then y plus delta y, we can write it as pi yx at location y multiplied by the area delta z delta x, and pi yx at location y plus delta y multiplied by area delta z delta x respectively. Similarly, x momentum entering the control volume at location z is pi zx at location z multiplied by delta x multiplied by delta y, and then the x momentum leaving in the z direction at location z plus delta z is pi z x at z plus delta z, and then multiplied by the delta x multiplied by delta y. So, actually what we are trying to do in this momentum equation, whatever we have written equation number 1, we are trying to get the individual terms. So, these terms we have written now just now, and then this term also we have written now. So, external force and then accumulation terms we write, and then substitute all those terms here in equation number 1. So, next is external force on fluid. Usually it can be gravitational force, electrical field, and then magnetic field, etc. If some reaction is there, so those parts will also come into the picture, but however let us consider only gravitational part. So, x component of external force on fluid due to the gravitational field is rho g x multiplied by delta x, delta y, delta z, it is shown here. So, and then accumulation is nothing but dou rho V x by dou t multiplied by delta x, delta y, delta z is the accumulation term. So, the net rate of addition of x momentum in all three direction is nothing but this is the net rate of x momentum in x direction plus net rate of x momentum in y direction plus net rate of x momentum in the z direction. These three and then plus this is the gravitational field, that is in the right hand side term we are having these terms of equation number 1, that is momentum balance equation, and then left hand side term is the rate of accumulation of momentum is nothing but dou by dou t rho V x multiplied by delta x, delta y, delta z. So, now these terms what we do, we substitute in equation 1 and then divide by delta x, delta y, delta z either side, and then we apply limit delta x tends to 0, and then we apply limit delta x tends to 0, limit delta y tends to 0, and then limit delta z tends to 0 either side. So, we can get this we can convert this equation into the partial differential equation as shown here. So, what we get after applying these limiting conditions, dou by dou t of rho V x is equals to minus dou by dou x of pi x x minus dou by dou y of pi y x minus dou by dou z of pi z x plus rho g x. So, this is the x momentum equation in Cartesian coordinate system having only gravitational force as external force. Now, what we do, you can we can write this similarly y component of equation of motion, right. So, then similarly if you write, you do not need to derive, it is quite similarly you can do this one. So, that would be dou by dou t rho V y is equals to minus dou by dou x pi x y minus dou by dou y pi y y minus dou by dou z pi z y plus rho g y. So, minus we can take outside. So, similarly z component of equation of motion is dou by dou t rho V z is equals to minus dou by dou x pi x z minus dou by dou y pi y z minus dou by dou z pi z z plus rho g z. So, rather writing these three equations, what you can do, you can write them as a kind of one single equation in vector tensor notation, that you can write it as dou by dou t rho V I is equals to minus del dot pi plus rho g I. So, this I could be x comma y comma z. So, without any subscript also you can write this equation as equation 10b, that is shown here. Now, what we do, we substitute this combined flux momentum flux tensor pi is there. What now we substitute for individual terms like convective component and then molecular mechanism component also we have to include now. So, what is pi? So, combined momentum flux tensor pi is the summation of convective momentum flux tensor rho v v and molecular momentum flux tensor pi. So, we can write it as whereas this molecular momentum flux tensor pi is there, that we already know it as tau plus p Kronecker delta. So, this Kronecker delta is equals to 1 if I is equals to j, it can be it is 0 if I is not equals to j. So, when you substitute this here in this term, then you get pi is nothing but rho v v plus p delta plus tau. Now, this equation you substitute in equation 10b, in place of pi you write this particular expression rho v v plus p del Kronecker delta plus tau. So, then we get dou by dou t rho v is equals to minus del dot rho v v minus del p minus del dot tau plus rho g plus rho g. So, this is the momentum equation in Cartesian coordinates. So, this is having all three components, x component, y component and z component we have written in a vectorial form. Okay. So, we can expand in three individual components also. This equation is known as the Cauchy's momentum equation. So, in this equation left hand side term is the rate of accumulation of momentum, is also known as the temporal term. Right hand side the first term is the rate of momentum addition by convective transport mechanism, is also known as the convection terms. Del p is usually known as the pressure terms and del dot tau is known as the viscous force contribution terms. So, combined they are known as the rate of momentum addition by molecular transport mechanism, and then rho g is the external force on fluid per unit volume. That external force here we have considered gravitational force. Now, if you expand this equation 12 in three different component like individual x component, y component and z component, you can see this equation. So, these equations are irrespective of the type of the fluid, whether Newtonian fluid or non-Newtonian fluid, irrespective of the nature of the flow, whether it is a laminar flow or turbulent flow or flow in transition conditions, whatever is the flow condition, whatever is the type of the fluid, these momentum equations are valid for all cases. Okay, they are not specific to any particular fluid, they are not specific to any particular nature of the flow, they are valid for all types of flow, they are valid for all types of the fluids. And then depending on the type of the fluid, one can substitute the corresponding tau expressions and then simplify the equations. Similarly, one can also derive these momentum equations for the spherical and then Cartesian coordinates as well. So, I have summarized here in cylindrical coordinates, r component of equation is given here, theta component of equation is given here, and then z component of equation is given here. Likewise, in spherical coordinates, this r component of momentum equation is given here, theta component of momentum equation is given here, and then pi component of momentum equation is given here. So, these are the equations of conservation of mass and momentum that we have derived in Cartesian coordinates, and then analogously we have written for the cylindrical and spherical coordinate system. And now, one not necessary to memorize these equations, but it is always advisable to remember at least equations in Cartesian coordinate system for those who are working in this transport phenomena area, for those who are doing research in that particular area. Okay. However, if you wanted to solve any problem, use these equations. These equations are in general provided or available any of the standard transport phenomena books. Any standard transport phenomena books, you can find these equations. Right. So, what is the point of this deriving these equations here? Like, let us say if you have a isothermal system and then you wanted to develop, like, velocity profile, and then you wanted to develop the volumetric flow rate expressions, etc. So, you do not need to do for each problem the balance, like you do not need to write the balance equations, balance equation for mass, balance equation for momentum for individual problems. Rather, what you can do, you can for any problem, you need to choose the coordinate system first, whether the Cartesian coordinate geometry is having the flow geometry for which you are solving the problem is whether it is in Cartesian coordinates, rectilinear coordinates, or is it in cylindrical coordinates, or is it in spherical coordinates. You have to find out, and then accordingly these equations you use, because these equations are nothing but those balance equations, and then from these equations you can strike off the terms which are not relevant to the problem you are interested in. Then you can have a final equation. That particular final equation, when you solve final partial differential equation, when you solve, you will get the velocity profile by applying the boundary conditions. Once you have the velocity profile, you can find out the volumetric flow rate as well. So, this is how this is the application, this is the use of deriving this equation. So, these equations we are going to use almost in all classes henceforth onwards after from the next module onwards. So, now what we do, we see the limiting cases of these equations. So, before going to the limiting cases of these equations, we are seeing so many time derivatives here, and then partial derivatives, different coordinate systems are given here. So, it is always advisable to have some kind of basic knowledge about these things. So, first we see partial time derivative. What does it mean by? What is the difference between partial time derivative and then total time derivative, right? So, rather mathematically explain it, what we do, we have a kind of example. Partial time derivative is, let us say you are sitting on the bank of a river, and then or you are sitting on a bridge, and then underneath a river is flowing. So, what you do, you concentrate on a particular location, fix the location, and then there are in the river so many fishes are there. So, right, you are intended to know the fish concentration in the region where you are concentrating, right. So, at that fixed location, with respect to time, you make count of the fish concentration, so that you can have the change of concentration of fish with respect to time for that particular location where you are fixing your target, right. So, that is nothing but partial time derivative, because here location is fixed. So, what is the fish concentration? These other surrounding locations in which for which you are not doing these measurements, you do not have any idea. So, since you do not have any idea about the fish concentration at other locations, this information is a kind of crude information, and then it does not give the true picture of the fish concentration in the river which in which you wanted to find out the fish concentration. So, this particular way of doing the time derivative is known as the partial time derivative, and then it is represented by dou by dou t. If the c is the fish concentration here, so we can write it as dou c by dou t at fixed location x, y, z. Now, you know that it is not true picture of the fish concentration in the river. So, what you do now, you try to improve your measurement, your fish concentration measuring you wanted to improve. So, what you do next, you take a boat and then go around the river from upstream to downstream, one corner to the other corner, the way you wish, and then try to cover as much the area as possible, right. And then at each location simultaneously you keep measuring the concentration of the fish with respect to the time as well. So, then whatever the final number that you get, the fish concentration by doing this way, that will be nothing but total time derivative, that is dc by dt is equals to partial derivative of the c plus dx by dt plus partial derivative of the c with respect to x plus dy by dt partial derivative of c with respect to y plus dz by dt partial derivative of the c with respect to the z direction. Now, this dc by dt total time derivative is the summation of the partial time derivative plus additional terms shown here, right. So, which are having the fish concentration with respect to the different locations as well, at different locations also it is having, right. So, definitely it is a better representation compared to the partial time derivative, but still it is not a reliable one, because this dx by dt, dy by dt and dz by dt are what? They are nothing but the velocity component of the boat in different x direction, y direction and z directions. But the whatever the velocity of the boat is there, that is not same as the river stream velocity. So, one need to have a better improvement. Take a canoe and sit on it. It is flowing with a kind of river stream velocity. So, you measure the fish concentration with respect to time at different location here also, and x direction, y direction, z direction, different directions you go, and then measure the fish concentration with respect to the time also. So, by this way, whatever the differentiate derivative that you get, that give the information about the fish concentration is known as the substantial time derivative, also written as the capital D by capital dt of c. So, this dc by dt is equals to partial derivative of fish concentration with respect to time Vx multiplied by partial derivative of fish concentration with respect to x direction, and then plus Vy partial derivative of fish concentration with respect to y direction, plus Vz multiplied by partial derivative of fish concentration with respect to z direction. Now, this is much better than the total time derivative. Why better? Because this Vx, Vy and then Vz whatever are there, they are the velocity component of the canal, which is same as the this reverse stream velocity component. So, this is giving better component, better representation of the fish concentration in the river. So, since here the this moving with the substance is there, that is the reason this derivative is given, the substantial time derivative. So, in the vectorial form it can be written as capital D by capital dt of C is equals to dou C by dou t plus V dot del C. Since it is about the material and then moves along with the material, it also has the name material derivative. Also it has the hydrodynamic nature of the flow. So, then it is also known as the hydrodynamic derivative, and then since it is moving following the motion, it is also known as the derivative following the motion. Different terms are given, different names are given actually. So, this substantial time derivative is much more reliable than the total time derivative, which is much reliable compared to the partial time derivative. So, the partial time derivative is the least reliable, least accurate, substantial time derivative is the most accurate. So, now after defining the substantial derivative, if you write the equation of continuity and then the equation of motion in terms of substantial derivative, you can write continuity equation as d rho by dt is equals to minus rho del dot v. Whereas, the momentum equation in vectorial form, combined momentum equation, you can write as rho dv by dt is equals to minus del p minus del dot tau plus rho g. So, these are the continuity and then momentum equations in terms of substantial derivative. Now, if you take a limiting conditions of the Newtonian fluid, so for the Newtonian fluid, in this equation, momentum equation, whatever the tau is there, for the tau you have to replace by this term, that is tau is equals to minus mu del v plus del v transpose plus 2 by 3 mu minus k del dot v and then Kronecker delta. So, now if you consider only first this first term of this particular equation given here, so then rho dv by dt is equals to minus del p plus mu del square v. Mu del dot tau is del dot mu del v is mu del square v plus this rho g gravitational term as it is. So, if you combine this del p and then rho g term and then you write it as capital del P. So, you can write this equation as rho dv by dt is equals to minus del p plus mu del square v is also known as the Navier-Stokes equation, is also known as the Navier-Stokes equation. Now, in the Navier-Stokes equation, if you do not consider the acceleration term, that is the temporal term and then this convective terms, that is whatever the momentum flux is there due to the convection, if you do not consider, then that equation Navier-Stokes equation can be written as minus del p plus mu del square v plus rho g is equals to 0, is also known as the Stokes flow equation, also known as the creeping flow equation. This has the important significance in the cases where the motion is very small, very small, almost stationary or moving with a very small velocity. So, such conditions are we can see in general in lubrication theory, particle motion in suspension, flow through porous media, etc. So, other extreme of this Navier-Stokes equation, if you do not consider the viscous forces, then you have rho dv by dt is equals to minus del p plus rho g. So, that is Euler's equation for inviscid flow. But in general, we do not experience fully inviscid or true inviscid flows, but in general there are also many cases where the viscous forces influence of viscous forces are almost negligible compared to the other terms of the momentum equations. So, this equation Euler equation is also useful in such applications such as in a flow around airflow wings, flow of river around upstream surface of bridges, compressible gas dynamics, ocean currents, etc. The derivation of this equation and other details of the different types of time derivatives, Navier-Stokes equations, all these details have been taken from this reference book Transport Phenomena by Bird, Stewart and Lightfoot. Thank you.